What chapter would this be?
I think, let's see. Yep, chapter 15.
Do you normally get to this point?
Yeah.
Or this is even past the thermodynamic, which you usually don't get to?
Yeah, typically, the fluid stuff is so brief that it was in the second semester course, and a student I did not have first semester asked how far we got in fluids, or did we cover fluids? And I said, yes, but it was probably so quick, students didn't notice. At which point, one of the students I did have the previous semester said, we did fluids. So. Yeah, and I still need to answer your question of what is actually expected for you to know from thermodynamics and fluids. But let's not answer it yet. Plenty of time, we have till next week sometime. All right, fluid, gas, or liquid. So let's suppose I have a container here. Not that. And I just want to sort of treat this as two different layers. It's all the same liquid, I just want to treat it as there's no flow going in between it. There, all the molecules are sitting there and just happily vibrating sort of in place. So let's do a force diagram. Treat those two rectangles as, I've got fluid, it has, but treat it as its own entity. What are the forces acting on these? And I'll call this literally 1 and 2.
Possibly weight.
Okay. So I got weight 2, weight 1, and I'll throw the earth in there. Weight 2, weight 1. I guess weight of container. Okay.
You have normal force.
It's like box on ground. All right, so I got a normal force acting here and here. And I've got a normal force acting up there, Y2 and Y2. And then YC and YC. All right. So there is a difference between Y1 and Y2, which makes sense. So if I look at this middle bit right here, I have Y2 minus Y1 minus W2 is equal to 0. And Y2 minus Y1 is equal to W2. And what is formula for weight?
Mass times gravity. Acceleration due to gravity.
Thank you. mg would have been fine. All right. So we have mg, except when we're dealing with fluids, generally talking about the mass of a fluid is less common. You generally talk about it in terms of density. And so what's the formula for density?
MV.
Not mg.
No, MV.
Oh. You'll have to work out then.
That's per volume.
Yeah, per volume. M over V. And so this now becomes density times volume times G. If we're looking at, so let's take a look at Y1 here. So Y1 I guess there's a force from here, there's the, basically, we have an atmosphere up there. Yeah, we are talking about fluid, there's something up here. So we have this pressure from up above. Why is it A for air? So we have this generic way of looking at it. So if I apply this to the top section right there, we'd have y sub 1 minus y sub a is equal to rho of section 1 times the volume of section 1 times g. In other words, the force down here, the force that's holding it up, is going to be equal to whatever the atmospheric force is times rho v1g. Oops, plus. Now, talking about force when you're dealing with fluids typically is not common. So we generally talk about it in terms of pressure. What's the formula for pressure? Not the ideal gas, just in general.
Would be force times area.
Or, it's time for you to do the same now.
Force over area.
Yeah, we go. It's the force per unit area. Our units of pressure would be the units of force over the units of area. What's the SI unit of force?
Units.
Area.
Meters squared.
So we have newtons per square meter, which was too much for physicists and scientists to write, so that's the Pascal. You've heard the height, did I do the hide and seek humor? Like, most physics humor, it is amusing, but not laugh out loud amusing. So Newton, Pascal, and Einstein are playing hide and seek. Einstein's turned to be it, so he closes his eyes, starts counting to 10. Pascal runs and hide. Newton decides to draw a 1 meter by 1 meter square on the ground and stands in it. Einstein gets to 10, turns around and says, Newton, I got you. And Newton says, no, I'm a Newton over a square meter. You got Pascal. And true to form, physics jokes. All right. So I have this pressure times the area, force is pressure times area. Well, I've got some area sitting up here. Think of it just as a normal cylindrical container here. Pressure times that area is equal to, so this is the atmospheric pressure, whatever it happens to be, times the area, is equal to the pressure from the fluid times the area plus rho 1v1 g. Actually, I want to get this back over there. So I have my atmospheric pressure minus my, I feel like I got it minus, oh, that's correct. This is not. I had to change some subscripts. Y1, that's the force coming up from below. That is the pressure at whatever depth that is, that's the pressure in the fluid, times that cross-section of area is equal to the pressure from the air times the area. Volume is just whatever that area is times the depth. So that area times that depth right there, which I will cleverly call Y. So this is the pressure of the fluid at some depth
times A is equal to the pressure from the atmosphere times A plus rho, basically the density of the fluid, times the volume of the fluid, which is just A times Y. G. A's cancel out. And we have the pressure of a fluid is equal to whatever the atmospheric pressure is, plus rho YG. Which means that the deeper you go, as Y gets bigger, the deeper you go, the more pressure you're gonna feel. Been to the bottom of a swimming pool? Did you feel that your ears hurt? It gets worse with age.
What was Y again?
The depth, it's how far down you go. Y is a positive number that's measured from here. So if I take an object and I have it suspended in a liquid, I know that the pressure here is greater than the pressure up here. So down here, there's some pressure acting on this. Actually, there's a force acting on this related to the pressure. That pressure is equal to, I'll call this pressure L for no 2. And up here, there's a pressure up here, P1. I'm making it look like pressure is a vector. It's not a vector quantity, but it plays one on TV. So I have my object up here. At this level, there's some pressure 2, pressure 1. Did I have the numbers reversed a moment ago? Well, it's here now then. So if I look at the forces acting on this, and just for the sake of simplicity, let's assume that it has some area right here, and it's the same area below. We can get into some real nasty stuff. Bringing in vectors, dot products, and so forth, but let's just simplify it. I have something that is symmetric, or even thickness all the way down. The depth of this distance between here, why don't we call this H? So if I look at the forces acting on it, if it is just sort of suspended there, I have its weight acting down. I have the normal force from the fluid, so I have a force upwards from the fluid, which I'll call F2 right now, and there's a force down coming from the fluid. If it is in equilibrium, then I know that the weight plus F1 is equal to F2. Weight is just going to be mg plus F1, which is the pressure coming from up there, which is the P1 times the area up there, is equal to P2 times the area down below. So my weight actually is equal to P2A minus P1A. The pressure, we just derived that formula, is going to be equal to whatever the atmospheric pressure is plus rho VG. We got past that. Rho YG. That's for the fluid. I'll call that Y minus times the area minus pressure from the atmosphere plus rho fluid Y1G. Y1 would be the depth from the surface to here, and Y2 to here. combining some stuff. Well, the atmosphere part drops out. I'm left with the density of the fluid, GA times Y2 minus Y1. Y2 minus Y1 is just the difference between these two depths right here, which is just H. So I have rho F G H A. Well, H times A, that's the volume of that cube. So this is equal to, so we have mg equals density of the fluid, G times the volume of, well, just Q or whatever I have fluid in it. If it's not an equilibrium, I still have that. Equilibrium has a set equal to the weight, but it's not an equilibrium. I still have this force right here, which is acting upwards because of the difference in pressure from the bottom to the top. This is the buoyant force. It is the weight of the fluid that's been displaced. So the volume of the cube, so that cube were actually made of water, that buoyant force is just the weight of that water that's gotten pushed out of the way. It's now FB top. So if we want to look at the buoyant force acting on me out here, sitting right here, my volume is approximately 0.1 cubic meters. The density of air, the fluid around me, is about 1 kilogram per cubic meter. It's 1 point something. G, well, we're doing crude estimations here, let's make it easy. 10 meters per second squared. So, the buoyant force acting on me is, well, just multiply it all together and you get 1 Newton. My weight is about 1,000 newtons, but air is supposed to meet up about a newton. So when you stand on the scale, then, well, first off, it measures normal force. If you really wanted to find out what your true weight was, Earth spinning about the axis, you are here at Winston-Salem, standing on the scale. Force acting this way is you have a gravitational force acting that way. You have a buoyant force acting this way. So you have weight, buoyant force, a normal force acting this way, and yep. So you're traveling around in a circle in that direction. So if you're acting going around in a circle this way, but the force is so far that way, there's got to be another force involved here that's keeping you from, because you're going to have a force in this direction and a force in that way. And those will have a force going this way and that way, this way and that way. This is going to be dominant. What keeps you from going to the equator? There's another force acting on you.
we've taken that into account, we've gotten that one into account, there's not another. No tension here, there's a buoyant force, we've got that. Yeah, there's a friction acting on you. And so really to do the proper, to figure out what your true weight is, you can calculate FB, except with better numbers. Normal force is what the scale's gonna read. Take the centripetal motion into account, there's a friction acting there. I mean, all in all, it's a fun little problem. But we will leave it on that note. I went through a problem like this in the video, so you can always catch it there. Wednesday will be our last lab. Monday, the last class, and then a week from Wednesday, final test. And then over Christmas break, you will just have to cry yourselves to sleep because you don't have physics at that moment. Or tears of joy because you had the experience of taking physics.